Hi everyone again. In this video we're going to talk about the quantum numbers and electron configuration of the elements. Okay, let's start with the quantum numbers. Principal quantum number is shown with n, and it indicates the energy level of the atom. In fact, it indicates the energy level of the electron that is found in this atom. So n can be the numbers 1, 2, 3, 4, goes like this. In fact, it goes till the end of 7 because in periodic table we have 7 periods. Or you can just show with the capital letters like K, L, M, N, which indicate the shell of these electrons. Okay, the second one is the azimuthal quantum number. It is also known as secondary quantum number. It is shown with small l like this. It shows the shape of electron clouds and it divides shells into subshells. So L starts from 0 and goes till the end of n minus 1. For example, if n is equal to 1, L can only be 0, which indicates the s type of orbital. Now, when n is equal to 2, L can be two values. It can be 0 or it can be 1. And if it is 0, this is the s type of orbital. This is the p type of orbital. So, which tells us in the first energy level, there can be only s type of orbital. In the second energy level, there can be s type and p type of orbital. And when n is equal to 3, L can be 0, L can be 1, and L can be 2. So this will give you s type, p type, and d type of orbital. So in the third energy level, you can have 3s, 3p, and 3d. And finally, when n is equal to 4, there can be L is equal to 0, L is equal to 1, L is equal to 2, and L is equal to 3. So which will give you s-type orbital, p-type, d-type, and now comes the f-type. So in the fourth energy level, you have 4 different types of orbitals: 4s, 4p, 4d, and 4f. Now remember, these are only the type of the orbitals. These are not giving you the number of orbitals. Okay, let's look at an example. If you have the K shell, this means that the primary quantum number is equal to 1, secondary quantum number can be 0, and type of orbital is going to be only s. When n, the shell is L, when n is equal to 2, then you have 0 and 1 as the secondary quantum numbers, and you can have s and p type of orbital. Now you have the M shell. This means that you are at third energy level for this electron. It can be 0, 1, 2 as a secondary quantum number, and the type of orbitals can be s, p, and d. And the third quantum number is the magnetic quantum number, which is shown as ml like this. Now it gives the position of the orbital relative to another one, and it divides subshells into orbitals in this case. Now first we have to calculate the number of orbital that belongs to a specific type of orbital. It is calculated by a formula 2l plus 1. Okay, look an example. If n is equal to 3, remember you can L is equal to 0, L is equal to 1. You can have also L is equal to 2. Now this means that you have s type of orbital, p type of orbital, and d type of orbitals. Now how many orbitals you have in these types? So in this case, you're going to use this 2L plus 1 formula. So for S, L is equal to 0. So when you put that 0 instead of this formula here, this L here, so you're going to end up with 2 times 0 plus 1, you have only one orbital. And P, 2 times 1 plus 1, you're going to have 3 orbitals. And D, 2 times 2 plus 1, you're going to find 5 orbitals. So for S, you have 1 orbital here. For P, you have 3 orbitals here. And for D, you have 5 orbitals here. So what about the ML numbers? In this case, ML will be equal to 0 because you have 1 orbital, no the other orbitals. So ML is 0. If you're talking about the p orbitals, in the middle one you have the value of 0, then this one will be minus 1, this one will be plus 1. And for D, this is going to be 0, plus 1, plus 2, and this is minus 1 and minus 2. So if there is F orbital, it is going to start from the minus 3, goes till the end of plus 3. And finally, spin quantum number, which is shown with ms here. An orbital can take at most 2 electrons. If one is on the clockwise direction, the other will be on the counterclockwise direction. Now, the reason is, in an orbital, you can have at most 2 electrons, and these electrons have the same sign, minus 1. So this means that they are going to repel each other. When they repel each other, they're going to turn on different sides. So when you indicate that spin quantum number, ms, you can have only 2 values. First one is plus 1 over 2, and the other one is minus 1 over 2. Okay. Again, this is like a summary of what we have all done. Now, K shell, n is equal to 1 and L is 0. ML is also 0. Types of orbitals and how many? It's going to only have S type and you have only 1 orbital. So what about the MS values? It can be plus 1 over 2, minus 1 over 2. And the maximum number of electrons that it can take, this is going to be 2. For this spin quantum number, I'm going to write all of it as the same here, because they're going to be rather 1 over 2 minus or 1 over 2 plus, so it doesn't matter. Now comes the L shell. L shell is the second energy level. It can have 2 possible secondary quantum numbers, 0 and 1. So this means that you have S-type orbital or P-type orbital or both of them. S-type can have the ML value of 0 and P-type can be minus 1, 0, plus 1. S, only 1 orbital again, and P, remember, 3 orbitals. S can take at most 2 electrons, and this can take at most 6 electrons. So when you sum them up, you're going to end up with the 8 electrons for the second energy level. Okay. M shell, this is the third energy level. The L values can be 0, 1, 2. ML values can be 0, minus 1, 0, plus 1. Why? Because this is S-type orbital, this is P-type orbital. Finally comes the D-type orbital. So this can start from minus 2, it goes until plus 2. S only have 1 orbital, P has 3, and D has 5. So this can take at most 2 electrons, this 6, and this will be 10, and this is 18 electrons. Okay, the last one, N shell. This is the fourth energy level. It can have the L values 0, 1, 2, 3. This means that you have S-type, P-type, D-type, and F-type of orbitals. And how many of them? 1, you have 3 here, and you have 5 here, and you have 7 here. So the possible ML values, the magnetic quantum number values, this is 0. This is -1 to +1. This is -2 to +2. And this one -3 to +3. So this can take at most 2 electrons. Now again 6, again 10. And what about this one? Is going to be 14. So when you calculate the total number of electrons that a specific energy level can take by using this formula here, you can calculate as 2n squared, so 2 times 4 squared, which makes 32. So when you sum all these numbers up, you're going to end up with the same numbers. Okay, let's look at finally electron configuration. Now the first energy level, you can only have 1s2. Second one, 2s2, maximum 2p6. Third one, 3s2, 2p6, 3d10. 4s2, 4p6, 4d10, 4f14. 5s2, 5p6, 5d10. It goes like this. Now 6x2 and 6p6, and it also goes like this. And you have, of course, 7s2 and 7p6 because we have 7 periods. So when you are writing the electron configuration, you're not doing just like reading a book, but you're just going down like this. Start from the 1s2, then comes 2s2, then comes 2p6, 3s2, then comes 3p6, 4s2 here, and then 3d10, 4p6, 5s2, and then 4t10, 5p6, 6x2, and it goes like this. So you're going to look at the electron numbers, and those ones are going to be your electron numbers, and you're going to sum them up and find the final electron configuration for an element. Now we have some rules while writing the electron configuration of a neutral atom or a cation or anion. Now the first one is the Aufbau principle. Electrons are located in the orbitals starting from the one nearest to nucleus and having the lowest energy. The second one, Hunt rule. Electrons are located in the orbitals having the same spin, having the same energy first, like 3p or 3d, one by one with the same spin, and the electron in each orbital is located with the opposite spin. Now, which I mean, for example, you have 2p4 here, and p has 3 orbitals. When you locate these 4 electrons, it's going to be like this. First, one by one with the same spin, and then you're going to put the second one with the opposite spin. Now, what is wrong with that? If you just put it like this, this is not a true electron configuration. If you put it like this, again, this is not a true electron configuration. But you put like this. Okay, this is correct. You don't have a problem with this one. The third one is the Pauli principle. Every orbital should take at most 2 electrons. Now, this is not the only principle. In fact, this is more than that. And those electrons cannot have the same quantum numbers. So this is really important. Let's give me an example from this one. For example, this is 2p4 and you have some electrons here. Now these electrons have the same principal numbers. they have the same secondary quantum numbers, they have the same magnetic quantum numbers, but what about their spin numbers? So you have two electrons in one orbital and they have opposite spins, so their spin quantum number will be plus 1 over 2 and the other one will be minus 1 over 2. So although they have three same quantum numbers, the fourth one will all be different. This one, the fourth principle, is modeling principle. The energy of orbital increases as n plus L value increases. So which I mean, for example, you have 1s, 2s, 3p, 3s, and 3p. Now this is n is equal to 1 and L is equal to 0. N is equal to 1 and L is equal to 0. So when you sum them up, it's going to be 1 here. 2s, n is equal to 2, L is equal to 0. When you sum them up, this is going to be 2. This is n is equal to 2, L is equal to 1. So when you sum them up, this is going to be 3. This is n is equal to 3, L is equal to 0. So when you sum them up, you're going to find 3 here. And finally, n is equal to 3 and L is equal to 1. When you sum them up, you're going to find 4 here. So when you just write the electron configuration, you're going to see that n plus L values increases. And last one, this is not a principle, but some kind of a term, spherical symmetry. If the last types of the orbitals in an electron configuration are half full or full, then the atom is said to be spherically symmetry. For example, if I write 2p4, the electron configuration is going to be like this. So this is not a spherical symmetry. But if this is 2p3, all the orbitals are half fulls, yes, this is a spherical symmetry. Or if you have 2p6, it is all filled up, so yes, again, this is a spherical symmetry. Okay, let's write the electron configuration for some of the atoms. Lithium, 1s2, 2s1. Beryllium, 1s2, 2s2. Bor, 1s2, 2s2, then comes 3p1. This is 1s2, 2s2, and 3p2. This is 1s2, 2s2, 2, let me erase this one, 3p, 2p3, 1s2, 2s2, 2p4, 1s2, 2s2, 2p5. This is 1s2, 2s2, and 2p6 here. So which ones show spherical symmetry? This one, this one, this one, and this one. Okay, now comes the ions. Now this is chlorine. It has 17 protons, meaning 18 electrons. So when you write the electron configuration, it is going to look like argon's electron configuration. So it's stable now. Sodium 11, 1s2, 2s2, 2p6, and 3s1. Now sodium plus 1 cation. Now when you remove one electron from an atom, this means that you're going to remove that electron from the highest energy level. You cannot just have this one electron from here, from here, from here, but here the highest energy level, the third one. So electron configuration is going to be just like the neon. Again, it's going to be stable. Now scandium 21. 1s2, 2s2, 3p, 2p6, 3s2, 3p6, 4s2, now comes 3d1. Now, okay, this is a neutral scandium. Now the next example is based on scandium plus 1. This is a cation here in this case. Now, from this previous electron configuration, you're going to just drop off one electron. Remember, you're going to drop it out from the highest energy level. not the last orbital in the electron configuration. So you're going to look at all these numbers, all these energy levels, and find the highest one. So this is the highest one, the fourth one. So this means that you're going to drive that one electron from here, and the electron configuration will be like 1s2, 2s2, 2p6, 3s2, 3p6, now 4s1, and 3d1. This is really important. Please be careful with the electron configurations of the transition metals. If they are a cation +1 +2 or something else. Okay, scandium 2+. Okay, again the same. 1s2, 2s2, 2p6, 3s2, 3p6. Now remember, you have 4s2 here. You're going to take all these electrons from here, and the electron configuration ends with 3d1. Okay, iron. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d6. Now if this is iron 3+, this means that you have to take off 3 electrons. Now these 2 electrons are going to be taken off from here and 1 from here. So what is going to be like? So this is all be vanished, and you're going to end up with 5 here. So final electron configuration will be like 1s2, 2s2, 2p6, 3s2, 3p6, and then comes 3d5 here. Okay, and we have some special electron configurations. So when you don't know the rule and write the electron configuration of chromine atom, it is going to be like 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d4. Now this is not the case, because if we have 4 electrons here, at the moment it doesn't show spherical symmetry, but if it has one or more electron in this 5th orbital, then it shows spherical symmetry. And being spherical symmetry gives an atom a little bit stability, not like the noble gas, but a kind of stability. So when you open the electron configuration of this chromine, this is not will be the case. You're going to just open it as 4s1 and 3d5. Just remember. So for the second example, if you drop off 2 electrons from here, this means that you're going to take one of them from here. So this 4s1 is going to be vanished, and one more from the last one. So it is going to be like 1s2, 2s2, 2p6, 3s2, 3p6. There is no more 4s here, but you will end up with 3d4. Now copper is an example, another example for the exception. In fact, copper ends up with 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, and 3d9 will be the case if you don't know the exception. But in order to have again a spherical symmetry in this part, one electron from the 4s2 jumps up to this 3d9, and it makes it as a 3d10 here. So what is correct about it? This is going to be 4s1, this is going to be 3d10. Okay, now this is true. And for the last one, if I drop 1 electron, so this means that you're going to drop it from the highest energy level, the 4th one. So there's not going to be any 4s here. So the electron configuration for copper +1 is going to be 1s2, 2s2, 2p6, 3s2, 3p6, and this is all vanished up, ends up with 3d10 here.